What could possibly beat the rocket equation? Refueling. To achieve higher velocities and reach distant destinations, space vehicles need to carry more fuel. However, this increases the rocket's mass, which in turn requires even more fuel to propel the added weight. This is an endless loop, a paradox that rocket engineers have battled for decades until the concept of refueling emerged. SpaceX's Starship promises to be the pioneering spacecraft to make this concept a reality, heralding a new era for the entire industry. So, how will this process be executed? And when is SpaceX expected to perfect it? Let's find out in today's episode. Starship is set to play a pivotal role in the Artemis 3 mission, slated for September 2026. To achieve this, SpaceX has made crucial adjustments to Starship's standard design, turning it into the Human Landing System, HLS, for the Moon. The challenge, however, is that Starship needs a massive amount of fuel, far more than it can carry when it leaves Earth. And that's where orbital refueling technology comes into play. SpaceX plans to launch a flying fuel depot, or an orbital gas station, to store the liquid methane and liquid oxygen that power Starship. They'll also launch multiple Starships just to fuel up this depot. The point is, refueling in space is no simple task. It's not like filling up a tank on Earth. In zero gravity, moving fluids requires advanced techniques and rigorous testing. SpaceX is gearing up for its first large-scale demonstration of fuel transfer between two Starships in orbit, and it's expected to happen as soon as next year. So, what exactly will they do in that test? Well, the plan for this demonstration is meticulously detailed. First, Starship, known as the Target, will be launched into orbit. About 3 to 4 weeks later, a second Starship, called the Chaser, will follow. These two massive spacecraft will perform an incredibly precise docking maneuver in orbit. Once they successfully connect, the Chaser Starship will begin transferring fuel to the Target. After the transfer is complete, they'll detach and both ships will return to Earth. The sight of two massive spacecraft docking in space will be absolutely epic. Nothing like this has ever happened before. But surprisingly, this isn't too difficult for SpaceX. Elon Musk confidently remarked, "It's basically just docking with yourself." Not trivial, but certainly easier than docking with the International Space Station, which is a lot more complicated. Pretty confident, right? The docking seems like it will be smooth, but the real challenge lies in transferring fuel between two spacecraft in orbit. No one has ever attempted to transfer cryogenic fuel from one spaceship to another in space. So, what might this process actually look like? Let's walk through it from start to finish. First, the two Starships will dock in a belly-to-belly configuration. This means they'll rotate so that their fueling ports are facing each other. These ports are similar to the ones SpaceX already uses to fuel Starships on the launch pad. Once they've securely docked, the ports will open, and specially designed fuel lines, built to withstand ultra-low temperatures and high pressure, will connect. Next comes the fuel transfer, the most critical step. The fuel will flow from one Starship to the other by using a pressure differential between the tanks of the supplying and receiving ships. According to Amit Kshatriya, head of NASA's Moon to Mars program, the basic flow mechanism is driven by the pressure differential across the umbilical. This follows a fundamental fluid dynamic principle. When there's a pressure difference across a pipe, the liquid or gas will naturally move from the area of higher pressure to lower pressure. This method is considered simpler and more efficient than using pumps. After the fuel transfer is complete, the valves will close to prevent any further flow. The connections between the two ships will be disengaged, the docking latches will release, and small maneuvering thrusters will fire to push the two Starships a safe distance apart. Finally, the main engines can be ignited to bring the spacecraft back down to Earth. Sounds easy, right? But this process is much more complex than it seems. One of the biggest challenges SpaceX faces is the boil-off phenomenon of the fuel. Let me explain. The liquid methane and liquid oxygen, LOX, used to fuel Starship are cryogenic liquids, meaning they need to be kept at extremely low temperatures to remain in their liquid state. Specifically, liquid methane must be kept at around -162 degrees Celsius, while liquid oxygen requires an even colder temperature of about -183 degrees Celsius. As the temperature rises, even by just a small amount, some of the fuel will shift from liquid to gas, a process known as boil-off. In the vacuum of space, without atmospheric pressure to help keep the fuel in its liquid form, this process happens faster and is much harder to control than on Earth. According to Amit Kshatriya, SpaceX is taking multiple measures to tackle this problem. Both ships involved in the refueling demo will have thermal insulation and vacuum jacketing around internal plumbing to limit boil-off. Otherwise, the demo itself will not be achieved, he explained. With this method, SpaceX can reduce the boil-off rate to a bare minimum, possibly around just 0.05% of the fuel mass per day. Another complex puzzle SpaceX has to solve in their demo effort is the fluid dynamics challenge in a microgravity environment. This isn't just a simple technical issue. It's a sophisticated problem in physics and control engineering. In a refueling scenario, The mass of the liquid fuel is often significantly greater than the dry mass of the Starship itself. This creates a unique situation. When the fuel tanks are not full and the spacecraft is in motion, the fuel has its own inertia and interacts with the walls of the tank. Unlike on Earth, where gravity pulls liquids downward, in a microgravity environment, the motion of the liquid is far more complex. The term sloshing is used to describe the movement of liquid within a container. In space, this phenomenon becomes particularly important. Any acceleration or deceleration of the spacecraft can cause sloshing. For instance, when the spacecraft decelerates to prepare for docking, the liquid will be pushed forward, similar to how passengers in a car are thrown forward during sudden braking. When the liquid hits the walls of the tank, it can create undesirable forces and moments that impact the spacecraft's direction and movement. To solve this, engineers developed a technique using ullage thrusters. These are small, specially designed thrusters that create a gentle push, just enough to nudge the liquid fuel toward the bottom of the tank, where the fuel transfer port is located. This ensures that the fuel is always in the right place to be pumped out efficiently. It seems like SpaceX has already cracked the code on overcoming all the challenges involved in the refueling process. So, how many flights will SpaceX need for this process in the context of Artemis 3? Given the current development pace of Starship and the schedule for Artemis 3, it's highly likely that they will use Starship V2 for this mission. According to SpaceX, Starship V2 will carry 1,500 tons of fuel to deliver 100 tons of payload into low Earth orbit. This means one refueling depot in LEO will have a capacity of 1,500 tons. Since each flight can carry 100 tons of payload, it will take 15 flights to fully refuel a Starship. To compensate for the boil-off during this process, an additional flight might be needed, bringing the total to 16. Add one flight to launch the depot spacecraft and one flight for the HLS, Human Landing System. And you're looking at 18 Starship launches for Artemis 3rd using Starship V2. Wow. That's a lot of launches. Pretty complex for just one trip to the moon, right? The number might go down when SpaceX moves to Starship V3, but that version isn't ready yet. Well, do you have any other ideas for reducing the number of launches? Comment below. Now, orbital refueling definitely demands a huge amount of technical effort, but once SpaceX pulls it off, they'll be opening the door to a new era of space exploration and off-Earth economic development. The most obvious benefit of in-space refueling is the ability to dramatically extend the operational lifetime of spacecraft. Right now, satellites and probes are limited by the amount of fuel they can carry from Earth. When that fuel runs out, the mission usually ends, and the spacecraft either returns or becomes space debris. With refueling capabilities, we could unlock longer-lasting satellite or deep space exploration missions. The ability to refuel in space opens up incredible opportunities for reshaping spacecraft design. Instead of a vehicle carrying a massive amount of fuel for the entire journey, engineers can focus on designing simpler spacecraft, increasing space for scientific equipment and useful cargo, and developing high-performance engines optimized for deep space travel. Once in-space refueling infrastructure takes off, an entirely new industry will emerge. You know, as we venture farther into space, the ability to fuel up a spacecraft will become as crucial as filling up a car on Earth today. This doesn't just pave the way for bolder exploration missions, but also lays the foundation for a true space economy, where humans can live and work sustainably beyond our home planet. All right, that's it for today. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more in-depth looks at the latest advancements in space technology. Thanks for watching, and I'll see you next time.